Hello, everyone. Welcome to the May 31st, 2024 working group serving meeting for Orchestration Workstream. And this meeting will be recorded and the recording will be shared afterwards. And keep in mind that this meeting follows the CNCF Code of Conduct. First of all, thank you, Kai, for inviting the reserve team to attend the meeting. And for those of you who are from the Ray or reserve team, would you like to quickly introduce yourselves? Maybe let's start with Kai.
Yeah. Hi everyone. My name is Kaixin, and I'm a software engineer in Nscale from the Ray core team. And I primarily working on the Kubernetes side, Ray on Kubernetes, and recently also working on some like the performance optimization for Ray core perspective. And I think we have several colleagues that joined this meeting. Edward and Alessi. Edward, would you mind introduce yourself?
Yeah, so I'm Edward. I also work at Anyscale, and I've been working on Ray for the past like 4 or 5 years. So I've worked on a lot of different parts of it, including Ray core and actually like our original ancient Kubernetes integration. And I'm also like the main maintainer of Ray serve.
Cool.
Oops.
Anyone else?
Yeah, it's me. My name is Alexei. I've joined somewhat recently, about a year ago in Scale. I'm working on the platform team and occasionally helping out on like other parts as well, including research.
Okay, anyone next?
I think that should.
Yeah, I think let's hope from the Nscale side.
Okay, cool. Then Edward, do you want to kick it off with your presentation?
Yep, sounds good. Okay. Hopefully you can see this, and you should be able to see full screen slides. Is that right?
Yep.
Okay, great. Yeah, so Kaishan and I are going to give just an overview of basically Ray serve, how Ray serve runs on Kubernetes, and then we have a few kind of specific pain points that Kaishan will go over at the end, and hopefully there will be some discussion there. I think overall getting through these slides will probably take like minimum 20 minutes or so. So in order for this to not be me boring you to death, it would be great if people, ask questions as we're going. If you're confused about something, if you're not sure, why something is the way it is. I know Ray on top of Kubernetes is a little bit different than other things that are kind of more like Kubernetes native. So please feel free to interrupt me. I can't see the chat, and I can never figure out how to do that in Zoom. So if anyone asks questions in the chat, maybe Terry, if you don't mind, like reading them out or something, that'd be good.
Sure. Can you see the hands?
Yeah, I saw you raise a hand just now, so
Okay.
I'll look out for that.
Okay.
But if I miss one, then let me know. Cool. Okay, so I'm going to start with just a brief overview of like motivations of Ray and kind of how it works. So, obviously AI is everywhere, especially generative AI last year, so it's been exploding. And Ray is sort of positioned as like the open source framework for like building end-to-end ML applications. So a bunch of logos that you probably recognize up here, and all of these folks are using Ray for some combination of training, fine-tuning, serving, data processing, really kind of the whole life cycle of ML or AI. So Ray is really kind of like this end-to-end solution, and we really focus on being like general purpose and not locking you into any specific like framework or hardware or anything like that. And it's built to be scalable, which is obviously important because like the data and compute requirements for AI are very high. So just to kind of walk through like the layering to build a little bit of a mental model, Ray comes with, there's basically like the Ray core layer, which is a pretty simple API that lets you just write like a basic Python program and execute that across a large cluster of machines or pods in Kubernetes. That can run on top of, cloud providers directly, such as AWS or Azure or Google Cloud, and can also run on top of just VMs or, of course, on top of Kubernetes, which is, why we're here today. And one of the things that's really powerful about Ray is that it comes bundled with a set of libraries that kind of target like each part of the ML lifecycle. So there are libraries for data processing, distributed training, hyperparameter tuning, reinforcement learning, and of course, online serving. So why do people choose to use Ray over alternatives or, including, building things themselves on top of just basic Kubernetes? So I think the biggest one is that it's really easy to use, and we've had like a huge focus on making it, basically making, distributed computing and like large scale hardware accessible. So you don't even really need to know anything about networking or gRPC or any of those concepts. And you can leverage like a 500 node cluster to run a distributed training program, or even write something more custom than that. So as I mentioned earlier, it's also very general purpose, which means that it can be used for the end-to-end machine learning AI lifecycle, but also fills in a lot of other gaps. Like if you're just trying to run generic Python, like distributed Python workloads, Ray is great. If you're building a new library because the existing ones don't suit your needs, we've had like many independent successful libraries written on top of Ray as well. So it's really it very general purpose, and you're not really worried about like running into a situation that it's not going to cover because it's too specific. And as I mentioned, the ecosystem is a large part of this as well. The libraries that come with Ray are kind of best in class for each specific use case. So you put that together in a whole package, and it's very attractive for a set of tools that you would use to build an ML platform on top of. So let's walk through just a little bit of like how a basic Ray program would work. So this slide says architecture, but obviously this is a code sample. So really simple piece of Ray code here. You can see on the first couple of lines, we're defining what's called an actor in Ray. So this is just like a regular Python class that can define some methods. It can have some internal state. And when you put this ray.remote decorator on it, that means that you can now schedule this to run anywhere across the Ray cluster. So to instantiate copies of this actor, we call this actor.remote, which is kind of a new injected constructor. We can also set options on this actor. For example, if it needs a GPU, or maybe you need to specify like dependencies that it requires, or you want to like customize where it gets placed, you can pass in a number of options here, and these can all be specified like directly in the code. And then in order to actually like invoke methods on that actor, you can just call the like method name .remote. So here I have a really simple example where we call this do work method on the two actors. Each of these returns a future, which is called an object reference in Ray, and then we just wait for those to complete. So this is, like a really simple example, but this can be extended to be sort of like arbitrarily complex. You can pass futures between actors. You can also mix this with stateless tasks, which are like more commonly used for data processing, kind of embarrassingly parallel workloads. So it's a simple API, but one that gives you a lot of flexibility to build on top of it. So let's walk through what this would actually look like if we were to run this basic program. So I have a copy of the program that we looked at on the left, and then sort of a basic architecture diagram on the right. So a Ray cluster is made up of essentially a group of nodes, and one of them is called the head node, which contains this special process called the global control store, which is essentially like a global scheduler that maintains like resource usage and is used to schedule things across the other nodes. The other nodes are called worker nodes, which will run actors and tasks. And all of the Ray nodes also have a Raylet. And the Raylet is, somewhat similar to the kubelet. So it basically maintains the resources and scheduling on a single node. So in order to schedule something on one of the worker nodes, you need to essentially go through its Raylet process. So if we run this program, then it would run as a driver script. So if you were to submit this as a job to the Ray cluster, it would likely run on the head node, and this driver script would execute. And the first thing it would do is make a request to the global control store to create these actors, actor 1 and actor 2. Once these actors are created, and I'm eliding some details here, so the global control store will handle the scheduling and get the actors placed, and they will start up. So once the actors are actually created, then executing tasks goes directly to them from the driver. So this do work.remote call, the driver will make a remote RPC to the actors to tell it, hey, execute this task with this method name and this input data. And then there are some, behind the scenes RPCs for basically communicating back the results of the futures. So of course, if this is running on top of Kubernetes, then the picture looks pretty similar. The main thing to point out is that each of these Ray nodes would be its own Kubernetes pod. So this is kind of the key difference, I think, of Ray running on top of Kubernetes versus a lot of other types of applications, which is, Ray is basically allocating this set of Kubernetes pods, but then scheduling like heterogeneous workloads dynamically inside of them. So for example, in this picture, you can see the head pod has this driver script and the global control store. Another worker pod has maybe 2 different types of actors, and you could have many, many more pods that are running different types of actors and tasks, and this really sort of like dynamic workload. So Kaishan will talk a little bit more about this later, but when running on Kubernetes, the main way that people do it is by using this kuberay operator. So in that case, kuberay will run as a controller, and if you want to start a Ray cluster, run a job, start a Ray serve service, then all of those go through like standard Kubernetes custom resource, like applying custom resources, which get reconciled by this controller. And it is the thing that's actually creating the pods, auto-scaling up and down pods, creating services so that you can send requests, and running the driver script in the case of submitting an offline job. I'll pause here for just a second in case there are any questions about this. I have a hand raised from Terry.
Yeah, I have a question. So, I remember, so there are basically two layers of auto scaling, right? Reserve has auto scaling for those deployments, Ray deployments, and kuberay also has auto scaling to scale the Ray cluster, right? Based on workloads. How do they work with each other?
Yeah, good question. So I haven't really talked about how Ray serve works, but it's not too different. But basically, you can imagine that any generic Ray workload, this driver is dynamically creating actors. And if this, say we have this picture where we can fit like 4 actors or something, this driver tries to create hundreds, then essentially what will happen is this global control store is exposing metadata about the like pending resource requests that cannot currently be scheduled. And there's a separate autoscaler process that will communicate that with the kuberay controller to actually like start new pods to satisfy those requests. So for Ray serve, the Ray serve controller is just like creating more actors, which then causes that process to happen. Does that answer your question?
Yeah, thanks.
Okay. David?
Yeah, thank you. Probably similar to the previous question, but I see this as kind of a scheduler on top of the Kubernetes scheduler. So in terms of parallel executions, I know that the Kubernetes API has some restrictions in terms of has some rate limits. So I'm wondering how the Ray control plane interacts with the Kubernetes scheduler, prevent the native scheduler, I don't know, limiting parallel executions in terms of number of pods or etc. I don't know if you get the question.
Yeah, Kaishan, do you want to take that question?
Yeah, honestly, I think the currently, I think currently the auto scaling, the scheduling that in the Ray and the Kubernetes, they are two level, and I think they control different scheduling units. I think a Ray is controlling the Ray task and actor. You can think it's like a function or a class, and the Kubernetes schedule control the pod. And you can think like I think as the word said is about that. Ray control like how to schedule the Ray test actor to a Ray node. But if the Ray test actor doesn't have enough resources to allocate a new Ray test actor, and the Ray hat will trigger the auto scaling, tell the kubelet to tell the Kubernetes API server to create a new Kubernetes pod. And for the Kubernetes pod scattering, I think a user can define like in their kubelet custom resource. You can define like the node selector or affinity, something like that. So it's I think the user of the kubelet and the user writes the JavaScript is a different perspective. Kubelet maybe is for the infrastructure engineer, and the JavaScript is mainly for like the platform engineer or the data scientist. Yeah. Is this answer your question?
Yeah, thank you.
Thanks.
Okay, we had a couple more. Matteo?
Yes. Hi. I'm wondering, a Ray worker could potentially have to run a lot of actors with very different resource demands. So how does kubeRay kind of determines what's the right size in terms of CPU, memory, GPU of all the workers?
Yeah, good question. So basically in the kubeRay custom resource, it specifies like worker groups that have like different shapes. And then the Ray autoscaler has basically like a bin packing algorithm that will determine like which resource shapes it needs and how many of them. So the intelligence for that actually lives like inside of the Ray autoscaler, which is like a hidden box in this diagram. But it basically bin packs the tasks and actors into the available resource shapes. Does that make sense?
Yeah, I have a quick follow-up question, and I'm assuming there's kind of the administrator that deploys Ray in the cluster who has to define all the worker groups with their characteristics.
So the worker groups, so you actually can define them per cluster, or you can at least like customize them per cluster, because sometimes it is important that like the shape of the worker group kind of matches the application if you're trying to like optimize it a lot. So it's not often the case that you would like have that defined globally for your cluster and then not customize it at all.
Okay, thanks.
And then another question from Abdullah.
Yeah, I have two questions. The first one is, did you think like of a integration approach with Kubernetes where the actors are pods rather than basically modeling the node as a pod here? I guess that's what you're doing with kubeRay.
Yeah.
But I was wondering if you thought about or discussed basically going one level below and model.
So it's a great question. I wrote like a long design document about this like 3 years ago internally, and it's like certainly that would be the way to make Ray like integrate as well as possible with Kubernetes. Part of it is honestly just that Ray was not originally designed that way, and it's like a really big lift in order to change it. And there are also some other unknowns, like for example, I am probably not going to be able to like recount the details very well now, but there were issues like, for example, with the Raylet being able to schedule a pod, like co-schedule a pod to the same worker. Like essentially this Raylet architecture just like didn't really work anymore if you're trying to schedule each actor or task inside of its own pod. So the answer is like, we've never seriously tried to do that, like really put a lot of resources into it. But I do think that it's like a really astute point, and it's possible that we could try to move towards that in the future to like sort of reduce the impact of the 2 layers of scheduling.
And another question related to the auto scaling aspect that you just discussed. You mentioned that it does bin packing. Does it do preemption? Does it try to do, for example, like defragmentation?
Yeah, so
or is
the
it like a time schedule?
defragmentation.
Yeah.
Yeah, so basically like active defragmentation.
Yeah.
So we don't currently try to do that for like generic workloads. For example, like just if you're like running a Ray core application, you're just like starting a bunch of actors and tasks. And the reason for that is because we don't like there's no notion of like a safe draining protocol or like a way to migrate actors. I think that's something that we've talked about looking into. We do have some logic to be able to do that inside of Ray Serve, where we do have kind of like more semantic understanding of the application. But for like generic Ray actors, it's difficult because they might have like some state and we don't know the impact of basically like preempting them. Cool. Okay, I think that's all the questions right now, so I'm going to move on. Oops. Okay, so yeah, what I was talking about up until now is mostly kind of Ray core. So let's talk about Ray Serve. So Ray Serve is the basically like online inference library that's built on top of Ray. It shares a lot of the same kind of motivations and like benefits of Ray core itself. So it's very Python native. So you can write a Ray Serve application that runs like multiple models or multiple like steps such as pre-processing and post-processing. And you can express that as like just one Python application, which I'll show an example of, I think, on the next slide. I think one of the things that people really come to Ray Serve for is for doing like multi-model inference and being able to like disaggregate CPU-bound work from GPU-bound work and IO-bound work. And we also, support like flexible scaling and resource allocation, which I'll show some examples of in a couple slides as well. And Ray Serve is, basically for deploying production Ray Serve applications. The 2 ways that we recommend doing it are on top of Kubernetes using the kuberay operator, which has a Ray service primitive, which is kind of like a managed Ray Serve application, or on top of Anyscale, which is like our fully managed solution. So here is an example code snippet of a Ray Serve application that consists of 2 what we call deployments, which might be confusing if you're very used to the Kubernetes terminology, that are making up like one application. So there is a predictor deployment, which is a Python class that's basically wrapping some kind of model, just like abstracted away here. But you define a constructor where you take in, maybe a URI, which is like a path to S3 or Google Cloud Storage, and load that model. And then when a request comes in, you basically just call that model on the input. Of course, there's probably some like better typing and like data munging here, but I kind of skip those details to keep the code sample short. And then separately, we also have a featureizer, which might be doing some like more heavyweight feature pre-processing. And in this case, the featureizer is taking what we call a deployment handle so that it can actually call into the predictor. So you can see that this deployment handle is passed in the constructor. And then when a request comes in, we can do some basic pre-processing locally. Or you could also imagine that this pre-processing could be like yet another deployment if you wanted to like fully disaggregate this. And then we call this deployment handle and we call .remote on it and pass in the input, and then we return the output from that. So these deployments are a little bit different than Ray actor because they actually could consist of, they're basically like a replicated set of Ray actors. So you can pass a number of replicas or an auto-scaling configuration. And when you make calls to them, such as with this .remote call, this is actually doing some somewhat intelligent load balancing across that set of actors. So let's take a look at what this would look like if you were to deploy such an application. I have another kind of similar looking diagram here, but now I'm not showing the Ray system processes, so just you can imagine that they're still there. So RayServe runs a set of actors independent of the application. So the first one is called the serve controller, which is basically in charge of deploying applications, making the auto-scaling decisions, starting actors, gracefully shutting down actors. It's basically the control plane on top of the Ray cluster. And then we also have these serve proxy actors that run inside of each Ray node. And these are the entry point for HTTP or gRPC requests that will route to the appropriate actors. So if you were to deploy the application that we looked at on the previous slide, there's basically this, the serve controller is, what actually takes the request to deploy, or would also return the status if you're trying to monitor the application. And then the serve controller creates Ray actors for each of the deployments that we had. So the featureizer and the predictor. You can imagine that these could also be replicated. So you may have, tens or hundreds of replicas running across many, many nodes. And then when a request comes in, the request first hits the proxy. The proxy then forwards it to the featureizer, and then the featureizer calls into the predictor. And these go over Ray actor method calls, similar to what I showed in the Ray core example. And these also support, they also return basically a future. So you can, very flexibly sort of chain requests and make a request into one replica, pass that result to another, and like pass it by reference to avoid excessive copying over the network as well. Yes, I have a question.
So the load balancing that Kubernetes is going to do is like Kubernetes doesn't know where the first featureizer is, right? Like on which exact Ray worker. So we have no idea where it is. And so it could load balance on the Ray worker too, right? Like it could send the request to Ray worker 2, like to basically serve proxy on Ray worker 2.
Yeah.
And then it goes to the featureizer and then goes back to the Ray worker 2, right? Like for predictor replica. So is my understanding correct?
Yes, that's right. So basically this proxy is will run on every node of the cluster that has at least one replica. And you're right that like Kubernetes load balancing, so there's basically like a service that points at these proxies, and that does not have is not locality aware, basically. So I think that's like one of the big kind of like technical gaps with running on top of Kubernetes in this way.
I mean, it's a technical gap in Ray itself rather than Kubernetes, because Kubernetes can target the right replica if the right labels are on the pod. It's the fact that you're not labeling the Ray workers with the labels that allows us to understand where the featureizer is, for example.
Sure. Yep.
So if you have multiple services running, like multiple Ray services running, you wouldn't know where it is, and you're always gonna hit. Like there's a high probability that you're gonna have like multiple hops, right? Like one extra hop at least.
Yep, that's right.
Thanks.
Jashin?
Yeah. I'm trying to add some comments. Technically, I feel the server proxies plays the similar role like crew proxy to do the like load balancing and handle all the like dirty works from the service mapping to the real function unit to serve the request, right? So yeah, I mean kind of I mean this is something pretty similar to the Kubernetes data plane traffic architecture. Yeah, so that's some comments.
Yeah, that's right. There is also a little bit of like application aware routing that happens inside of this proxy. So for example, RayServe has support for this thing called model multiplexing, where basically you can host like a very large number of models and sort of dynamically load and unload them. And the proxies have basically like model-aware routing, where they will try to prefer replicas that already have a model loaded. So there's a little bit of intelligence that lives inside of this proxy, which is one reason why it exists and is not just like we don't just route directly to the replica. Vaibhav?
Yeah, so also about things like batching, can you talk about, does that happen at the serve proxy layer, or is there another layer where things like batching happen?
Yeah, so it depends a little bit. So the batching pretty much entirely happens inside of the replica. So they're basically like two threads running in the replica, and one of them will batch requests until like some limit or like some timeout, and then it will like feed the batch to the actual method that's doing the inference. So that's like how it works if you're using the like RayServe built-in batching. For kind of more advanced batching, like for example, for LLMs, you can do more dynamic batching where you like you can start requests immediately, and then if a new request comes in, you can like dynamically add it to the batch. So those are handled by like the framework running inside of the replica. So for example, VLLM is often used with Ray, and VLLM just has like an asynchronous API where as soon as a request comes in, you enqueue it, and then it does the batching internally.
Okay, but the things like does the serve proxy then maintain any of metrics related to things like queue length or request failures or anything of that sort?
Yeah, so it does maintain metrics like just purely for observability, and it also maintains queue length metrics. Queue length is actually what's used for auto scaling in Serve right now. So each caller is basically pushing aggregated queue length metrics to the controller for auto scaling decisions.
Oh, thank you.
There's
Connor?
one more question from Chong.
Hey, yeah, I have a slightly different topic. I'm curious to know, how do you upgrade a Ray cluster? Like, do you upgrade the head and workers independently, like similar to Kubernetes, you can upgrade the control plane nodes? How does that work?
So currently, Ray does not support like rolling updates currently. So if you're updating the Ray version, you need to just stand up a new cluster. So for like batch workloads, this is kind of no problem because for the most part, people are running ephemeral clusters. So they just start a new Ray cluster, like run a job or like a couple jobs and then shut it off. For serving, obviously it's a bigger problem. So currently the kuberay operator will basically stand up a new cluster and then shift traffic towards it. If you're only doing an application level upgrade and not like updating the Ray version, you can do an upgrade within the cluster. But for Ray upgrades, yeah, you have to do like cross cluster.
I see. Okay. Thanks. Quick follow up on that. You said if I were to upgrade the Ray version, then the kuberay operator handles traffic. Like, are you talking about the kind of the control point operation traffic, like interact with Ray control plane, or like I'm talking about the inference case, right?
Yeah.
Or the inference application traffic.
The application traffic. So I'm gonna pause on this, and I'll have Kaishin talk about it in a little bit because he has some slides on it.
Okay, thank you very much.
Cool. All right, let's move on. So yeah, I just want to highlight a couple of like key features of sort of why people use RayServe and how it kind of differentiates. So I think the first one is, similar to Ray, it's very Python native, and there's a big focus on usability. So you can run a RayServe application entirely on your laptop, and you can like spin it up, send HTTP requests to it, and this includes like the disaggregating across multiple processes and things like that. And you can do orchestration with an imperative API in the code. So you're not trying to like declare what your pipeline looks like in YAML. That was something that like very early on we saw as a big pain point for people, that they preferred kind of the programmability. And we've also made some decisions to integrate with like really popular tooling such as Fast API, which people love because it's just like really user-centric. and pedantic and sort of like modern tooling that just provides a good developer experience. I think this is one part of it. The second part is it allows you to do model composition and sort of like disaggregation without having to split your code up into like multiple artifacts or multiple like microservices that you need to like deploy and manage and operate independently. I think, you know, the microservice model is kind of, in a way, it works really well, but for a lot of, you know, smaller teams or people that don't have infrastructure expertise, it can be really daunting and hard to operate. So a lot of our users like that they're able to sort of get the benefits of like distributed computing and disaggregation without kind of needing to opt into like more operational overhead. And yeah, the last thing is there's a lot of kind of like flexible resource allocation features. So you can do fractional GPU support. We do request-based auto-scaling, which is quite important because a lot of our users are not like the metrics-based auto-scaling, like CPU, GPU utilization is great if your applications are like really well tuned and you have a really good understanding of the performance characteristics. But that's really not the case for a lot of the applications that we see. So request-based autoscaling works really well, especially in the case where you have like dynamic batching and stuff like that. And we also support scale to zero, which we've seen as a like really common feature request kind of across online inference, as well as the model multiplexing support that I mentioned a couple of slides ago. Oh yeah, so one just kind of like public example that we have of this is, so Samsara is a pretty big Ray-serve user. So previously they had a bunch of different microservices that had been like written by various people at various points, and they had like slightly different deployment processes for all of them. And the big issue was they found it really hard to evolve this, because if they wanted to change like any part of, you know, how they're splitting the services or how they're scaling them, or like change the logic in one of them, then testing was like a really big problem, and they needed to coordinate changes between like the actual code and the DevOps side. So they really kind of felt like stuck. And then they moved this pipeline from being like these 3 separate microservices into like one Ray-serve application that they're able to test locally. And you know, basically one person could pretty easily make a change end to end. And they're also able to do some more like resource disaggregation. And after making this change, they were able to basically have like a 50% cost reduction overall for operating this pipeline per year. Okay, Kong, your hand is still up. Did you have a new question, or is that from before? Okay, cool. All right, so at this point, we have a little over 15 minutes left, so I'm going to hand it over to Kaishin to talk about some of the kind of pain points that we see with KubeRay.
Yeah. I think maybe can I share my screen? Oh,
I can just click through it. It might be
okay.
annoying.
Cool. Yeah. I think the first one that this is some context is about the Ray service CRD, and because I think this is a CNCF community, so I think everyone know what is a CRD and the operator, and you can think like a Ray service CRD is the CRD for the Ray serve, and we have the Ray cluster CRD. And how do we do the upgrades that? We will create a Ray cluster. And then when someone upgrade the Ray version, we will create spin up a new Ray cluster. And when the new Ray cluster is ready and all the server application on it is ready to serve requests, we will update the Kubernetes service and to switch the traffic to the new Ray cluster. So it is a blue-green upgrade strategy. But I think currently is that the user want to have like incremental upgrade, because you can think like if we need the H100 GPU to serve some large language model, if you so want to use the blue-green upgrade, they need to have the other H100 GPUs. So they require 16 H100, and most people cannot cannot have the 16 H100, so it will start there. So one of the points that we want to implement is the incremental upgrade. I think, and one of the pain points that because the Kubernetes doesn't native support the traffic split. Edward, could you move to the next slide? Yeah, and so here is that. We also consider to use the Kubernetes Gateway API. Yeah, but I think we have a long discussion for a long time, but because I think introduce a new dependency is always a very pain point for an open source project. I think if there are some like important feature that depends on another dependency, I think it will be pushed back by a lot of users. So one of the requests is that can the Kubernetes service to support like we can split the traffic. For example, this 5 endpoint that have like the 40% of the traffic, and next 6 endpoint that has the other 60% of the traffic that in the same Kubernetes service, so that we can control the traffic split that in a single Kubernetes service. Yeah, so I think this is one the first point for us. Jiaxin?
Hey, Kai-Shun, you like to talk about those the potential solutions for each like challenge, or you like to finish your slides and we can have some discussion later.
I think both are fine. You can ask your...
Okay. Okay, let's talk about this one. I think yeah, technically right, like the survey, there's no way to do that. I think the statement is correct. So a lot of like solutions, I mean the third party like add-ons on Kubernetes, they kind of support the canary rollout, right? So basically the service, we still create a different service to control the traffic rather than use one umbrella service and split the traffic underneath, for example, at the canary deployment or canary replica set level. So do you consider to use a different service? Because like Kubernetes have all the controls over the resources it created, right? So in that case, if you have a different like a canary service, let's call it a canary service, then technically you can achieve similar like canary rollout, like what for example like Argos or other solutions did. So I think yeah, like Terry have a lot of experiences on the Argo side. Yeah, if you have comments, feel free to add.
So
I am not pretty understand about Argo. I don't use it by myself, but I heard about a lot of people use that. And I think in my understanding, I think all the Kubernetes rollout solutions that it's based on assumptions that all the paths that in the deployment or in the replica set, they run the similar, they are monolithic and they run the same set of the application. But I think in the race that an application is across multiple nodes. For example, an application include like the model A, and the model A output will be the model B and the C input. And the model B and the model C output will be a model D input. And the model A, B, C, D can be all the different nodes that in the same red cluster. So we cannot tear down a array node because we didn't know which array serve replica or which model is running on this array node. So that's why we need to spin up a new array cluster.
yeah, I think what Jiaxin was saying is like having a new service for the new cluster, and then you have like another like load balancing layer that's like splitting across the two services. So that is indeed what we recommend people to do. But the problem is like we don't want to add a dependency on like a load balancer because we kind of can't really make that opinionated of a decision because it just won't work for users because they all have like different infra and stuff that they're used to running. And there's also like there's not really a standard like primitive or API that we can use like so that people could plug in their own load balancers without using the gateway API essentially. So it's like if we were just building something for ourselves, then we would do what you suggested, but making it like a framework that others can use is pretty limiting right now.
I see a lot of hands raising up, but we only have like 10 minutes left. So I'm wondering whether like those questions can be like whether we can have like a follow-up session for these kind of questions, so that Kai can finish his slides.
Okay.
Yeah, that sounds
thank
good. We have a few more, so let's do that.
Okay. Next slide. Thanks. And then the other side is that because for the reserve, if we want to achieve the reserve high ability, we require external Redis as the metadata store, because the default meta store in the array is the in-memory. So, but there are some concern about the external Redis. For example, this company doesn't use the Redis. And the second is that if they want to use like a cloud provider's Redis service, and some user complain that it's pretty expensive, or if they want to operate that the Redis by themselves, and the operator database is pretty hard. So is there any like the a KV store solution that's natively built in the Kubernetes, for example, like etcd? I think Flink use the etcd as their storage that for the Flink on Kubernetes. So I'm not sure is this the correct pattern, or is this an anti-pattern? So and if we can use the etcd as our metadata store, I think we can achieve a high ability very easily for user that's in their Kubernetes cluster. Yeah, and next slide. Yeah, and this one is that Reserve has a feature is that we will launch the container that's in the array pod, and this is because that because the array is very versatile, we can run different kind of application on it, different model, and we don't want to back all the information into the array pod image. So if we can launch the container in container, we can just pull the image whenever we need to serve the model. And one of the questions is that how can we safely use the image catching that's in the same Kubernetes node, so that the container in container can launch very fast. Yeah, so this is another question. I think we can mount like some file descriptor, but but I think some user will push back because it is not safe for don't fulfill their safe security team requirement. Next slide. Yeah, and I think this is we talk a lot about that. It's a two-level auto scaling, array controller, array test, and the actor scheduling, and the Kubernetes controller the pod scheduling. And you can consider one of the cases that for Reserve, we want to spread the same Reserve replica across multiple AZ to achieve the higher ability. However, that we need to create the you can see like this is the step one is that we need to create the like a GKE or EKS node pool that across multiple AZ, and then we need to configure the array path that with like the node selector or affinity, something like to schedule a path to the corresponding nodes, and then we need to configure the array CR that correctly to tell the array node that this node belongs to which AZ, and then user can write their array script to schedule their array sub replica that's on the different AZ. So we just wondering that is there any easy way to do that? For example, can pod that inject the AZ information that's into the pod, so that array can easily read that. So let's get this kind of information. Next slide. Yeah, and I think this is for like the multi-host and the multi-host TPU. And I'm not sure like does the super part, GPU super part has a similar issue or not. I think currently is that it requires you to set up some variables for the same path that's in the same Kubernetes worker group. Kubernetes worker group you can think similar like the replica set. So all the configuration in a single worker group should be the same. However, it requires us to set a different value of the pod. And the second one is that Kubernetes need to create a headless service, because all the TPU know that all the TPU pod that in the same pod size require know the different all the other paths DNS name. I think current solution is that GK built a webhook for the kubelet to set up this. But I think this is not a very scalable solution. For example, if in the future, if there is a new architecture, new protocol, or different kind of accelerator, I think it's hard for us to build a new webhook for the different accelerator. Yeah, so next slide. Yeah, and I think for the Ray autoscaler is that, as I mentioned, that there's a worker group which is similar to the replica set, and you can define like the GPU worker group or CPU worker group. This is a passback, and currently is that a user want to use a different kind of Kubernetes workload API, like a replica set, deployment, default set, or they also want to use the third-party workload API like the clone set. However, one of the blocker is that because Ray autoscaler need to delete a specific part, but like the replica set deployment doesn't native support that. So this is a blocker. Yeah. Next slide. Yeah, I think we are just very quickly go through the slides, and if there's any question, we still have a couple minutes, or we can or Terry, maybe we can have a way to do some follow-up.
Yeah, we can schedule a follow-up, but we still have 4 minutes, so we can still answer some questions, I guess.
Yeah, cool. Any questions?
Okay, it seems like those questions can be long.
If like some of the issues that or the pain points that you mentioned, I think we need to clarify like what Kubernetes is designed for and what it's not. Like for example, the for the storage, right? Like Kubernetes is not a database, so it's not positioned as a place where you're storing, like offers you an API to store data, arbitrary data, right? And etcd in upstream Kubernetes is just an implementation detail. Like in some cloud providers, they could use something different that is probably more efficient. So there is no explicit contract that tells you, oh, here's an API that you can use to basically store it on our on Kubernetes backing storage solution. So I think that like if you want to make progress on that direction, you would want to stop thinking of it as a Kubernetes pain point, more of like, okay, how can we offer like, a solution for Ray for the storage piece that is like, community maintained. Like in Kubernetes upstream, we chose etcd, and that's like what we offer, for the Kubernetes control plane. But again, as I mentioned, this is an implementation detail. At least that's my point of view. Like, so at some point you want to start thinking about, okay, how do we solve it in Ray, rather than continuing to think that this is a pain point or something that the lower level orchestrator needs to provide to you.
Got it. Yeah, I agree that I think it's not a common pattern to use the etcd. Yeah, but I just chat with like the some Think community. They just let have Think use it as the etcd, use etcd as the extension.
Because depending on the use case, like if you're using it for example, for KV cache sharing, like you wouldn't want to have it in a cold storage or like something. You might want to store it in a like distributed memory store on the cluster, right? Because you want something much faster.
I think it's not for the KV cache. I think it's just store some Ray metadata.
No, I understand, but you mentioned KV cache.
Oh, I just pronounce incorrectly. Sorry about
that. I have another point, but I want to open the floor. Don has a hands up.
Okay. Don. Okay.
We can't hear you, Don.
1 second. Can you hear me now?
Yeah.
Okay, cool. Thanks, Edward and Cashin, for this presentation and really informative. at least to me. And I think I talked to the Karen and a while back, and I think a lot of things. One thing I don't want to say, like the Kubernetes is evolving, can be changing. And the pinpoint, like of some of the pinpoint actually even came from me originally. So that we could, like for example, especially today's the Edward gave the presentation about the reserve architect and also the things. And I that's kind of the make me think about we need me be more thinking about how we change dynamic change, allow some of the part API change, right? So and another thing it is, Kaishan also mentioned that store to store the external store or to storage to store those the metadata. Actually, this is the part of. Have you ever think about this? Just using etcd, but it's not the etcd control plane. You could just using anything, include after etcd as the stateful set to store your metadata. And this is kind of more on the re-architecture, how you are thinking. So we can talk about those kind of things. And I just want to say that how much we can change of the architecture and how much we can change of the Kubernetes to generate of the abstract to you and make your support running on top of the Kubernetes is more easy. This is kind of fundamental things we want. This like the serving group and to try to thinking. So that's the things I just want to say. But any things we can discuss. But at least at CD and using Kubernetes control plane at CD to store I think that's not what you want, because you basically want to decouple those kind of things, generate off the abstract layer on top of that one. So Kubernetes can support your abstraction, right? So that's kind of things. So we can separate off the infrastructure layer from your distributing language framework, something like that. So that's what I want to share. And then maybe we need more brainstorming and how to evolve Kubernetes and how to evolve RAID together.
Yeah, cool. Yeah, thanks.
Thank you, Don, and thank you, Edward and Kai and everyone else for the discussions. I hope this is helpful and we can keep the discussions going, and maybe Kai and I can schedule another one in the future for more like a deep dive into these challenges you have and see if we can figure out a solution together.
Yeah.
All right.
Thanks
Thank you, everyone.
everybody.
Cool.
Have a good weekend.
Thanks.